Hi, and welcome to video lecture 2. This is the second of the two video lectures on preliminaries and building blocks. Building blocks, the sort of stuff that can underlie all the stuff we do in this course. Now, I said in the introduction to this course that you can go in different orders, and at this point, if you're really interested only in linear systems of equations, you can safely jump ahead to part 4 of the class on linear algebra. There'll be some stuff that might be a little confusing, but the stuff we're going to do in this video lecture on functions and limits and continuity and so on is not necessary for getting an understanding of linear algebra, matrix multiplication, and stuff like that. So at this point, if you're interested primarily in linear algebra, you can safely jump ahead to part 4. You miss a few things in there, but by and large you should be okay. Here, assuming you're stayed, we're going to be talking about functions, relations, utility, limits, sequences, series, continuity, and other important concepts relating to the representation of things like preferences or causal relationships in terms of functions. So we're going to start by talking about functions, and this module is the first of several relating to functions directly, and this module is about the definition of functions and basic properties related to them. Okay, so what is a function? Intuitively, a function is a mapping from one thing to another. Mapping is a sort of formal mathematical term here, but all it means is a way of connecting one thing to another thing. That's all it is. A way of connecting one thing to another thing. It has a very particular way of writing it, mathematically, but it looks like this. That's a function, f to be read f of x. So the function is f. It's a function of x, meaning you put some x into the function and it spits out something else. So all a function is like a machine. It takes as input some stuff. It could be a single x. It could be more than one thing. It takes as input something else, some input variable, and spits out an output variable for you. That's all a function is. It's a machine that takes in one thing and spits out another. We call that a mapping because it maps the values you put in to values that you get out. You can specify a function a little more formally by adding some things. That colon here is sort of like a such that again. But here it tells you what it's mapping. It's going to map some input set, say x, to some output set. Here we'll say the real numbers. This kind of function is very commonly used in political science because it represents a utility function, and we'll talk about that more in a later module in this video lecture series. But that's all a function is. It's a mapping from one set to another. The more general version looks like this. It's mapping from set A to set B. Set A here is called domain. The domain of a function is very important because it tells you what input variable range, I shouldn't say range because it's used elsewhere, what input variable go into the function itself. The functions are only defined over their domains. In some cases, the domain will be all numbers, but in some cases, the domains are only specific regions of numbers. For instance, we mentioned the logarithm before. This is a function. It's the logarithm of x. If you plug in values of x, it spits out a logarithm. If you have a calculator or a calculator in your computer, you can put a number in, hit the log button, it'll spit out a number. For instance, we said that the log of 1 equals 0. So the log takes 1 as an input and spits out 0. Log here is not defined for numbers less than 0. For numbers less than 1, it gives you negative values, but the log is not defined for negative numbers here in the real numbers. So if you're dealing with real numbers, you could not define the domain of the log would not include negative numbers. So we might say this: the log of x is a function that maps the positive numbers, positive real numbers, to all real numbers. That's why we've defined the log formally, and it tells you what the domain is. The domain here is all the types of input variables that can go into the function itself. Input variables that are not in the domain cannot be plugged into the function because the function is not defined over those variables. Okay, so that's what this thing is, the domain. This is the codomain. It's the set of all things that the function could map the domain into. So in the case of the top function here, the codomain is the real numbers. The real numbers, the function maps input variables x into anything that's a real number. You could have other kinds of codomains. They could be, you could map your preferences over eating into the set of all possible foods in existence. The codomain, the function must be defined over every element in the domain, and only those elements. The function does not need to produce every element in the codomain. It can produce only some of them. When the function only produces some elements, we call the elements that are produced by the function the range or the image of the function. The range or the image, these are equivalent here. And here's an example to show you what that means. We might make a function like this. Let's say we have a function that equals x squared, and it maps the real numbers to the real numbers. So it takes in real numbers for x and it spits out real numbers. What would we do with that? Is it all real numbers? Well, we can put in any real number here in the domain and we can get a number out. But if you notice, we can't get out every real number. Because it's x squared, it's x times x. Because two negatives make a positive, and two positives make a positive, you can never get a negative number from x squared. Therefore, the range of the function is not all real numbers, it's only the positive real numbers. So the codomain is R, the real numbers, but the range is only the positive real numbers. Well, including 0. We'll just include them 0 for now for the sake of this example. So the range can be a subset of the real numbers, of the codomain rather. In this case, the range is the same as the codomain, it's all real numbers. Sometimes it's really, the range can be very small. Here, the range is 3, the number 3. You can get nothing else from this function but 3. It's a constant function. So that's the range, and this is, those are sort of the major definitions here. Now what do we use these things for? Okay, well, start over here again. We use these things to represent many different things. In all cases, we use them to represent the transference or the assignment of something to something else, right? That's the mapping. In utility theory, in game theory, you use functions to represent preferences. Hi, sorry about that, some minor technical difficulties. So, as I was saying, one way you use functions is in utilities to represent preferences. And we'll talk about that more in a later module. But as an example, you might have 3 objects you care about. Say an apple, a banana, and an orange. Right? And we can write that like this. Right. Here's apple, banana, and orange. I might want to represent preferences in some fashion. Now we can talk about like apples better than bananas, better than oranges, if that's what I do. But we might want to assign some kind of numbers to those. So what can we do? Well, we can have a function, and we can say the function of an apple is, say, 3, and the function of a banana is, say, 2, and the function of an orange is, say, 1. And then say, well, the apple has a higher number. Right? This is basically what utility theory ends up being, assigning utilities to various elements of some set. Here the set is fruit, and we're mapping it to real numbers. But we can also do other things with these with functions. And another common thing you see in political science is the use in statistics and statistical models. To understand that better, we need to associate these functions with variables. So how do we do that? Well, let's call f of x y. Let's call f of x y. And let's say f of x is some nice linear function for the moment. We'll talk about linear functions in a later module. But let's say the function is, say, beta x. Remember, we can use Greek letters occasionally here. This matches the common usage in statistics. Let's say it's beta x plus alpha. Actually, it's an affine function, but it's good enough. So we have beta x plus alpha. Well, what does this mean? Well, here's your f of x. X here represents the independent or exogenous variables, the variables that are supposed to describe other stuff via their actions and their variation. The y here represents the endogenous variables, the dependent variables, the one that is affected and changed by the independent or exogenous variables. Right? So I change x and y changes. This is a function, and we represent the way in which x affects y by a function. And each of these representations encapsulates different substantive meaning. So for instance, if let's say x is the degree to which you're a democracy, and assorted measures of that, like polity, run from -10 to 10. So -10 to 10 x can be, right? Well, if I make it like this, then my theory, if the model is like this and says that some element y, say degree to which you engage in civil conflict, say, right? If it's like this, then the degree to which I engage in civil conflict, y, is dependent on the level of democracy, x, in a linear fashion. It's lowest or highest at one end of the scale and the reverse at the other end of the scale. So, for instance, if beta is negative, then I get a lot of conflict at the low end and much less conflict at the high end. On the other hand, if I have this model, then what I'm saying is that the degree of conflict varies in a nonlinear fashion. If beta is again negative, then this term is highest at 0 in the middle of the scale and lowest at -10 or 10. You can plug it into C. -10 squared is 100. 10 squared is 100. If this is negative, that's a negative 100. That's a big number. At 0, this is 0, a much smaller number. So in that case, you're telling a different story. You're telling a story about democracy or autocracy, strong autocracies or strong democracies having very little conflict internally, whereas middle countries having a lot of conflict internally. There are different stories, and they're represented by different functional forms. So functional forms basically can let us represent different stories and different theoretical models. Right. And that's typically how we use it in political science and social sciences in general. Okay, the last thing I want to mention now is how to represent these things graphically. Graphical representation can be really helpful. Some people learn better graphically, so it's especially helpful for them. But in general, it's good to have some visualization of your data, of your function, and so on. So how do we graph that? Well, here we typically have the y-axis be f of x, or y. The x-axis be x. And for each point in the domain on x, we plot the associated point on the y-axis, f of x. So if the function is f of x equals x, then it looks kind of like a straight line like that. Here's 1, and so on. If instead it's a function, say f of x equals x squared, and the domain is all numbers, then it looks kind of like that. I'm going to apologize, I don't draw these things well freehand, but I think it's better to do it this way. So it looks kind of like that. It's a U-shaped curve. It's smallest in the middle and highest in each direction as it goes away from 0, just like the function we used in the previous example. So all you do is basically plot for each point in the domain on the x-axis, the associated point on the y-axis, and that's it. Now, before we move on, I just want to mention one more thing. these are all functions of one variable. Functions are more general. So for instance, I could write a function of two variables, and maybe this has certain interpretations. It says that that the function is increasing in x in both ways, one by itself, and also increasing in an interactive fashion with z. The bigger z is, the bigger it increases with x. So the marginal change in the function with x is increasing in z. This ends up being very important for a lot of research, but we don't cover this until part 5 of the class. It's covered in the beginning of part 5 of the class on multivariable calculus. So if this is your interest, you might want to finish looking through all these building block lectures, first 2 lectures, and then take a look at part 5 and the stuff associated with multivariable functions. But it could be some tricky because some of the stuff in there is calculus related. For most of the stuff we're going to do until the probability section, we're going to be doing it with one-dimensional functions. Okay, well, that's it for Module 1. Thank you, and I'll see you in Module 2.